So you have 25 mils of 0.1 molar sodium hydroxide and 25 mils of 0.1 molar HX. Okay, but this time you have a weak acid, and Ka of the weak acid is 1 times 10 to the negative 5. What's our reaction here? HX plus hydroxide will give you 1. H2O plus X minus. What's the equilibrium constant for this? When you're neutralizing, let's see if we can construct this from two reactions. You have HX gives you H plus X minus. What's the KEQ for this one? This is Ka of HX, right? And what's the other reaction we can use? We can use the autoionization of water. So you have H plus hydroxide gives you H2O. What's the KEQ for this one? 1 over KW. Right? So if you combine these two, what do you get? H plus cancels out, and you got the reaction you want. So what's the KEQ for this reaction then? K would be equal to Ka of HX divided by Kw, right? Or here, times 1 over Kw. So what's the equilibrium constant for this reaction then? What's the Ka of HX? 1.0 times 10 to the negative 5th. And what's 1 over Kw? 1 over 1.00 times 10 to the negative 14. This gives you 1.0 times 10 to the 9. Okay, is that a large number or a small number? Large. What do you expect this reaction to do? Anytime you titrate a weak acid with hydroxide, typically you would have a reaction that pretty much goes all the way to completion. You have a large KEQ. Okay? So our we've solved our K here to be Ka over Kw, which is going to be equal to 10 to the 9. So let's solve this problem. Again, set it up as using initial concentration, changes, and equilibrium. Okay, so I is stable. What's our starting HX? 25 mils times 0.1 is how many millimoles? 2.5 millimoles. What's the total volume that we have here? 25 and 25, 50 ml total, okay? So 25 millimole, okay, let me make that. 2.50 millimole out of 50.0 mils. What's my initial hydroxide concentration? Same thing, right? 25.0 millimole out of 50.0 mils. What would be my change? What's my initial X minus? 0, right? What would be my changes? Minus X, plus X, correct? But what's my X going to be? I know it's going to be a complete reaction, right? Pretty much. So I'm just not going to do it that way. I'm just going to say minus everything, right? And how much of this would I make? This is plus everything, which is 25.0 millimole out of 50 mils. Okay? So at equilibrium, what do I have left? Trace amounts of this. I'm going to call it X. And this would also be X, trace amounts. And here, what's 25 out of 50? That's 0.05, right? Moles per liter. So how do I solve for How do I solve for this? For the pH? I'm going to say that 0.050 over x squared is equal to KEQ, which is 1.0 times 10 to the 9. Actually, there should be a minus x here. Why? Because if you have trace amounts here left, then this is not fully 0.05. This is 0.05 minus x. Okay, so there's a minus x there, but we're going to ignore that because we know that that's going to be a small amount compared to 0.05. So to solve for x, what do you get? X squared equals 0.050 divided by 1.0 times 10 to the negative 9. 0.05 divided by 1 times 10 to the negative 9. 10 to the 9, sorry. 1 times 10 to the 9. Equals 5 times 10 to the negative 11. Okay, and so x will just be equal to square root of that, 7.1 times 10 to the negative 6. 7.07, let's keep an extra digit there. 7.07 times 10 to the negative, what was it? Negative 6. So that's your x. If you know x, what is that x? That's hydroxide, right? If you know hydroxide, what can you do? How do you determine pH from hydroxide? You can go POH and then go from POH figure out pH, or you can just go straight to H plus, right? H plus would be what? 1.00 times 10 to the negative 14 over hydroxide, which is 7.07 times 10 to the negative 6. So 1 times 10 to the negative 14 divided by 7.07 times 10 to the negative 6 equals 1.41 times 10 to the negative 9. And your pH is going to be equal to inverse log of that. So take the log, the log of, negative log of that. So log times the negative of that, that's 8.85. So you can see your pH is basic at the equivalence point. Okay? Why are we saying this is at the equivalence point? You have equal moles of H plus and hydroxide. Okay? So if you did this titration, you did a titration curve for this, you're going to get something like this. This is pH versus volume of titrant. You're going to get a big jump, but your equivalence point is actually going to happen above pH 7. Okay? And you can explain that because you're saying, all right, pretty much what you have is you're out of HX. What you really just have is the conjugate of HX, which is a weak base. So X minus will give you a trace amount of, so a small amount of sodium hydroxide, and will give you it will hydrolyze. Okay, so you say your X minus. The way you explain that basic pH at the equivalence point is, at the equivalence point, you say the major species that you have is X minus, and that reacts a little bit with water to give you HX plus hydroxide. And so that explains your basic pH. Okay? So that's what happens at the equivalence point. Now, is there another way you can solve for the pH? You can go with the POH. Be a quick review. How do you get POH? Minus log of 7.07 times 10 to the negative 6. So you say 7.07 times 10 to the negative 6. Log of that, take the negative, that's 5.15. Oops. And so your pH would be 14.000 minus 5.15. So 14 minus 5.15 is how much? 8.85. So either way, you get the pH. Okay? So that's the equivalence point. So hopefully I've given you enough examples of these so that you can solve just about any problem dealing with equilibrium. It's not really possible for us to go into all the possible equilibrium problems. Okay? So keep in mind what you really need to do as far as problem solving strategy is write the reaction. Okay? And then get the KEQ. And if your KEQ is very large or very small, you're in luck. You can make simplifying assumptions. If your KEQ is not very large or very small, then you might have to go into actual solving of the polynomial, solving for the roots of your polynomial. Okay?